right, so last section we're going to take a look at is 4.2. We're going to do it over 2 days. We'll do the first part today, second part next academic week. And it's on doing some sketches. Okay, so when we're graphing rational functions, it can be a little bit tricky because we've got asymptotes and different things we have to figure out. Could have holes in the graph, and we got to figure all of that out. Okay, so I'm going to show you some different ways that you can go about sketching rational functions. Okay, so one thing we have to remember is when is there a hole versus when is there an asymptote. So any value that causes you to divide by 0, first of all, is undefined. Okay. But when you're graphing, there's really 2 different ways undefined can look. You can have a hole, which means you have a common factor in the numerator and denominator, or if you don't have a common factor, you get a vertical asymptote, which is very obvious to see. So let's graph this and see what happens. First, well, before I graph it, what value would you plug in for x that causes this graph to be undefined? Yep? 1. Okay, so 1 is where it's undefined. Am I going to have a hole in the graph at 1? Or am I going to have a vertical asymptote at 1? Yep. I'm going to have a hole. Yep. So when we graph this, I'm going to type it in parentheses, x minus 1 divided by x minus 1. And if you divide 2 things that are the same, what do you get? 1. So what would you expect this graph to look like? Yep. A horizontal line at what number?
1.
At 1, yeah. The only thing is it's going to have a hole in it. So it's a horizontal line at the number 1, but there's a hole at 1. So the calculator doesn't sketch the hole. Maybe if you zoom in a lot, I think somebody did see it if they zoomed in. There is a hole right there. Now, if I graph this one, what value is this undefined for? Marcelo? It's undefined at 1. Hole or asymptote when we graph it?
Hole.
Yep, it's going to be another hole. And if you simplify that, what would that simplify to? X minus 1 squared divided by x minus 1. Yeah?
Would it just be x minus 1?
Right, it's basically going to turn into 1 copy of x minus 1, because you have 2 in the top and 1 in the bottom, so 1 will cancel. So it's going to look like a line with a slope of 1 and a y-intercept of negative 1, except it'll have a hole in the graph at 1. Okay, so I'm not going to draw that one, but that's what it would look like. Okay, so both of those graphs have holes in them. Okay. You can call it a hole. The fancy word for it is it's called a removable discontinuity. Remember, discontinuity is a point in the graph that you have to lift your pencil. And removable, basically, you can kind of think of that as fixable. Right? So like, this was like a road, and you have a small hole in it. Well, that's easy to fix. Right? All you have to do is patch that hole, and we're good. With a vertical asymptote, think of that as a road. And you're trying to get from one side to the other. Well, that's a big problem. Okay? You can't just fill in a little hole, patch something, and make these 2 pieces connect. Right? So a vertical asymptote is not a removable discontinuity. You can't easily make these 2 pieces connect by just filling in a hole. So then what we do, if we want to get rid of a removable discontinuity, is we say, okay, you can use the formula everywhere except where there's a hole. And where there's a hole, I'll just tell you what value to use instead. Okay? That's what you would do. So if I wanted to, let's take this top one. And let's say that I wanted to graph this, but I want to fix the hole in it. So I basically want it to look like y equals x, y equals 1, okay, this top one. Well, if I want to fix the hole, but I still want to use that, I don't want to just say y equals 1. Okay, I want to use what they gave me. Then I could say this. I want you to graph x minus 1 over x minus 1 as long as x is not 1. You can use this formula everywhere that x isn't 1, and you'll get the picture, most of the picture that I want. There's one problem, and that problem is when x equals 1. So I'll just tell you what value to use that will make it continuous. When x is 1, I want you to just graph the point 1. So it's like graphing 1, 1. Okay, so the top part of the graph gives you this. That's what this gives you. So we graph that section everywhere that we are not equal to 1. And then where we are equal to 1, I have to pick a value that would make it connect. Well, if I pick 2, well, then it would be up here. I don't want that. That wouldn't make it connect. That's why I picked the number 1, because now I filled in the hole. So that's how you can take a function that has a removable discontinuity and fix it. You just say, all right, use that function most of the time, and wherever you had a removable discontinuity, just redefine it and say, use this number instead of the original formula, and it's like we just filled in the hole. Any question on that? So if I did this bottom one, let's look at that one. So let's say I want to graph that, but I don't want there to be a hole in it. Then what I would do is write it as a piecewise function and say, use that whenever x is not 1. Okay, so there's our graph. Now, when x is 1, what do we use? Well, we've got to pick a number that would make it continuous. Okay, so we kind of have to think about what this one would look like. Y equals x minus 1. So you've got a y-intercept at 1. And what's your slope? Yeah. Slope is 1. So right 1, up 1. And from there, go right 1. Let's see. No, I wouldn't be there. I would be there. And if we draw it, our graph would look like that, except when we're at 1, right now, we have a hole. That's the graph of this top piece. What value would I want to pick so that when x is 1, it fills in the hole? Oh, all right. So what value would we need to use to redefine this function when x is 1 so that we make it continuous? Well, just pick a number and we'll try it. 1. Okay, so when x is 1, let's try 1. So I use that line for the top piece, and when x is 1, I graph 1. Okay, so did we fill in the hole and make it continuous? No. Anyone have another guess at how we would redefine that function to make it continuous instead of having a hole? Yep. 0. Yeah. This time, when x is 1, graph the point 1, comma 0. If you graph that point, you just filled in the hole in the graph. Okay, so that's how you can tell when you have a removable discontinuity. You can just redefine the point at one value, redefine the function at one value, and it becomes continuous. All right, so that's what a rational function looks like in general. Just some polynomial in the top, and then another polynomial in the bottom. What's the end behavior model of what's in the top? Nice.
Would it be like PAX?
What would it be?
It would be like the A sub n x and so
A sub n, keep saying the rest of it?
it's A sub n times x to the nth power.
To the nth power, yes. That's the end behavior model of what's in the top. That's the highest term. It's the term with the highest exponent. What's the end behavior model of what's in the bottom? Oh, Jake? Say, yeah, b sub what?
Subscript
Yep,
x to the n.
x to the m. That's the end behavior model of what's in the bottom. So we know how to find the EBM of a polynomial. It's the highest degree term. I circled the one in the top, I circled the one in the bottom. Now, I want to find the EBM of the entire thing. So what do you think I'm going to do with these two EBMs to get the EBM of the entire fraction? Yeah, we're going to divide them. Yeah. So finding the EBM of a rational function just means find the EBM of the top, find the EBM of the bottom, and then divide the two. And that'll give you the EBM for the entire thing. And remember, when you divide them, because you're dividing, we're going to be using the same variable, that you're going to have to subtract your exponents. So like if you have x to the 5th divided by x squared, we should be writing that as x cubed. Okay. And then the coefficient that goes in front, well, it's going to be the coefficient of the EBM from the top divided by the coefficient of the EBM in the bottom. And that's the EBM for the whole thing. So what does the EBM tell us? What is the end behavior model used to figure out? Yep.
Isn't it to like how many times it crosses the x-axis?
Nope, it's not used to tell you how many times it crosses the x-axis. It might tell you something about it, like if you know you had an odd degree polynomial and the end behavior one's up, one's down, and it's continuous. That could tell you something about how many times at a minimum it has to cross. But we're not dealing with continuous functions anymore. We're dealing with functions that can have holes and asymptotes. So just knowing the EBM wouldn't tell us how many times it crosses anymore. So what do we use the EBM to do? Yep.
Would it be for like the end directions? Like would it be like if it's odd, it goes like up or down, and if it's even, it goes either down, down, or up.
So you're looking at the behavior where? Where are you focusing on?
Like the coefficient of the EBM.
So like where in the graph are you looking? Like the EBM is telling you what's happening where in your picture.
Like the edges.
At the edges, right? That's the whole point of an EBM. It tells you what's happening on the edges of your graph. When you look at the edges of your graph, what is x approaching? On the edges of your graph. Yep. Infinity or negative infinity. And what kind of asymptote do we figure out by letting x equal infinity or negative infinity? Yep.
Vertical.
Nope, that's the zeros of the denominator. So,
Horizontal.
horizontal, yeah. So the EBM is going to be the way that we can figure out the horizontal asymptote now, because it tells us what's happening on the edges of the graph. And that's exactly what happens when you let x equal infinity or negative infinity. So the first step to finding a horizontal asymptote is going to be now find the EBM and then look at the EBM, and that will tell you your asymptotes. Okay. So let's see if we can get the EBM of this one. What's the EBM of the top? Josh?
2x squared.
Yep, 2x squared. And what's the EBM of the bottom? Yep,
3x cubed.
3x cubed. Okay, we need to simplify that as much as we can. When you simplify it, don't leave negative exponents in your answer. If you're going to have a negative exponent, put the variable in the bottom of the fraction. So what does that simplify to? That's
It'll be 2 over 3x.
2 over 3x. Yep. That is the EBM. So now, if you want to figure out your horizontal asymptote, you have a very simple expression to look at and do it. You no longer have to look at all of this to figure out your horizontal asymptote. Okay? Because normally I'd say you let x approach infinity and then tell me what's going to happen. Well, if you look at this fraction and you don't do the EBM, watch what happens. What happens in the numerator as x approaches infinity? What does this approach as x gets bigger and bigger? Declan, what do you think?
Infinity.
Yeah, as x gets bigger and bigger, the numerator approaches infinity. What about the denominator? As x gets bigger and bigger, what does the denominator approach? Yeah?
0. Or negative.
So like if you plug in 1,000 for x here, it would get close to 0 in the bottom.
Infinity.
Yeah, the bottom would approach infinity. So now if you look at it that way, we have a problem. The top is approaching infinity, the bottom is approaching infinity. Now we have to try to figure out which one is approaching infinity faster. Well, it's the bottom. So the bottom is ultimately going to win out. But if you just find the EBM, you don't have to think through all that stuff that I just mentioned. Look at your EBM, and now let this value approach infinity. You only have one x to look at. You don't have multiple x's. As x approaches infinity, what happens to my denominator in the EBM? Just the denominator. Marcelo?
It's bigger.
It gets bigger. So now, what happens to the entire fraction? Jackson?
Gets bigger.
If the bottom of a fraction is getting bigger and bigger, the entire fraction is not getting bigger.
Oh, smaller.
It's getting smaller. And what's it approaching?
0.
Yeah, it's approaching 0. Perfect. So that is your horizontal asymptote, whatever number you're approaching. In this case, it is 0. Anytime you end up with a variable in the bottom of a fraction, that will always cause the fraction to approach 0 when there's a constant in the top and an x in the bottom. So that's how you find your horizontal asymptote. Let's try this one. Okay. What's going to be the fraction for my EBM this time? You don't have to simplify it yet. I just like to know the first step, and then we'll simplify it in the second step. Yep.
2x to the 4th over 3x.
Okay. And now when you simplify that, what do you get?
2 over 3.
2 over 3. That is your EBM. Okay, now to find the horizontal asymptote, you do the same thing we did in the last problem. Look at your EBM, find the x, and let x get bigger and bigger. And then tell me what happens to the entire thing in that box. Okay, so there's your EBM. Let the x get bigger and bigger, and tell me what's going to happen to the number in that box. Yeah, question or maybe a thought?
Is it just going to stay the same?
It's going to stay the same. So what's your horizontal asymptote in this problem? As an equation. Yeah.
Y equals 2/3.
Y equals 2/3. As x gets bigger and bigger in this fraction, there is no x. It's 2/3. It stays as 2/3. Okay. So whenever the degree in the top matches the degree in the bottom, the variable is going to cancel out, and you're going to still get a horizontal asymptote, but it won't be at 0. The only way that it can be at 0 is if which degree is bigger. Top or bottom? Yep. No, if the top is bigger, then we're going to start to get into slanted asymptotes or even curved asymptotes. That's going to be next time. So the only way you can get a horizontal asymptote at 0 is when the bottom has a bigger degree. Because what happens when the bottom is bigger? All the letters cancel from the top, and all you're left with is letters in the bottom. And a letter in the bottom always causes the fraction to go to 0. Okay. So for today, the degrees are either going to be bigger in the bottom or equal in the top and the bottom. In both of those cases, you still have horizontal asymptotes. When the top is bigger, then things get a little more complicated. Yeah.
You had already answered my question.
Okay, so we're going to look at sketching graphs where the degree of the numerator is exactly what I just said. It's less than or equal to the denominator. We're not going to do when the degree in the top is bigger today. Okay, so these are general suggestions. Sometimes they apply, sometimes they don't. Finding intercepts. Okay, that can be helpful to sketch your graph. When wouldn't it help? If your graph doesn't have any intercepts. Like the parent function, 1 over x. That function has asymptotes on each axis. It never crosses any of them. So you're not going to be able to find intercepts necessarily on every graph. But if you can, sometimes that is helpful to do. The other thing that we want to find next are the vertical asymptotes. Vertical asymptotes are the zeros of the denominator as long as what? When would a 0 of the denominator not be a vertical asymptote? Remember we talked about dividing by 0. It's always undefined, but sometimes it's a vertical asymptote, sometimes it's a whole. I'm just asking when it would be a whole.
When there's a common factor.
When there's a common factor. Okay, so as long as the zeros of the denominator don't also make the numerators, then you have a common factor. Okay, Next thing we're going to do is find the EBM. Say the EBM, what is that helpful for? Getting your horizontal asymptote. So these asymptotes, once we sketch them, it's going to give you kind of like grid lines on your paper to sketch your graph. It's going to give you some boundary lines. So you're going to have all your asymptotes sketched by the end of step 3. And then we're going to look at what happens near the vertical asymptotes. So if we had a vertical asymptote at 3, what do I mean by near it? I want to know what happens just to the left and just to the right. So just to the left of 3 would be like 2.99. Just to the right of 3 would be like 3.01. When you're near a vertical asymptote, what does your y value always approach? One of two things. Yeah?
Infinity and negative infinity.
Infinity or negative infinity. That's what I'm trying to figure out in step 4. Which one is it? Right? Am I up really, really high, or am I down really, really low? A lot of times, on one side of the asymptote it's high, the other side is low. It depends which side is which. Okay, so we can use the graphing calculator and the table feature to help us with step 4. And then once we've done all that, we should be able to do a pretty good sketch, and we can double check it on the calculator. Okay, so let's do some sketches. Remember, degree in the top will always be equal to the degree in the bottom, or degree in the top will be smaller than what's in the bottom. If it's not, you do not have horizontal asymptotes. That's next thing. Okay, so sketch a complete graph. What's something we might want to do with the denominator first? Because that's definitely going to help us when we need to find vertical asymptotes. Yep.
Factor.
Yeah, we're going to have to factor it right away. Worst case scenario, we need to use quadratic formula, but hopefully not. How does the denominator factor? Yep.
X plus 2,
X plus 2, x
X minus 3.
minus 3. Looks good to me. Yep. I don't see any common factors there, so I know there's no holes in the graph, just vertical asymptotes. Okay, so step 1, let's see if we can find some intercepts. To find the x-intercept, that's when you plug in 0 for y. So this side, this is my y. If I set this fraction equal to 0, that will give me my x-intercept. What's the only way that a fraction can ever equal 0? Yep. Yep, if the numerator is 0. And what value would make the numerator 0 in this case? Yep. 1. Just check that, make sure 1 doesn't cause you to divide by 0, because then that would be an issue. No, it doesn't. So this will cross the x-axis at 1. Okay, so I can put that point there. Let's find the y-intercept. Y-intercept is when you plug in 0 for x. Okay. If I plug in 0 for x, what do I get in the top? Yeah, that's -1. And what do I get in the bottom? Yeah, -6. So this graph has a y-intercept of 1/6. That doesn't tell me a time, but I got 2 points on my graph. Okay, so I've got my intercepts. Now I want to figure out my vertical asymptotes. Where are my vertical asymptotes in this problem? Dart, my vertical asymptotes. Oh. Yep, -2 and +3. So I'm going to put in 2 vertical lines, one at -2, one at +3. Also, when you are sketching a graph, you never cross a vertical asymptote. You can't, right? So that tells me right away when I sketch this graph, it's going to be in 3 separate pieces. All right, so I got my vertical asymptotes. Let's find the EBM to see if there's a horizontal. Let's try actually writing. EBM. Okay. What's my EBM going to be in this case? Oh, Ethan.
X over X squared.
Yep. And what does x over x squared reduce to?
1 over X.
1 over x. Okay. So now we got the EBM. So when you let that fraction, let the variable approach infinity, what does your EBM approach?
Negative.
So when this variable approaches infinity,
0.
your fraction approaches 0. That's going to be your horizontal, and you absolutely can cross a horizontal asymptote. No issue with that at all. All right, so let's put that in. Now, I need to figure out what's happening near each asymptote. So to do that, rather than plugging in numbers, I'm going to use the calculator, use the table, and let that figure it out for me. So x minus 1 divided by x squared minus x minus 6. Okay, our 2 vertical asymptotes were at -2 and 3. We can confirm that, because if you type those in, you get errors. Let's start with -2. We know we're going to be approaching infinity and negative infinity. We've got to figure out which side is which. Let's start with a number a little bit smaller than -2 to the left. What's a number that's just a little smaller than -2? Rush? I'd like to be within, like, really close, within like 100th or 1,000th. Sure, -2.001. I'm way down at -600. So as you approach -2 from the negative side, it's way down. Okay. What's way down going to be? Well, I'm going to do way down like that. Way down. Now, usually it's the opposite, but let's check the behavior on the other side. Jaden, what's the number that's a little bigger than -2? Yep, -1.99. And if we type that in, we're way up at +600. So that's the other side of my asymptote. Let's do the same thing for the asymptote at 3. Number a little smaller than 3, 2.99. We're going to be way down. 3.001. We're going to be way up. So it's down on the left, up on the right. Down, up. Now, if you want to get another point, we can do another point. But in the middle, I can kind of see what's happening. In the middle, I have to stay close to each vertical asymptote for as long as I can. Okay? So I have to stay very close, but eventually I have to start to curve away from it because I need to go through those 2 dots. But I can't just keep heading to the right because I run into another asymptote and I can't cross it. But I have to connect to this dot down here. So it's going to have to do something kind of like that. There's the middle. Now, on the right and the left, let's see what's happening there. Another good value to pick over in this section would be like 1, 2, 3, 4, maybe like 5. Plug in 5 for x. Almost 0. Okay. just a little bit up, point 3, we'll call it. So 1, 2, 3, 4, 5, just about there. That's enough for me to see what's happening in the upper right. I have to stay close to that. I have to curve down going to the right. Then I run into that horizontal, and it's going to look like that. Okay, we can do the same thing for this lower left section. -1, 2, 3, -4. That would be a good value to check. It's just about 0. It's negative 0.36. So 1, 2, 3, 4, -0.36. Oh, right there. So this one is going to stay very close to the vertical, start to curve away, but then run into that horizontal. And that's what this one looks like. Let's confirm it by looking at the sketch. I didn't get it quite as flat as it should have been maybe in the middle. Mine's a little bit steeper, but I mean, we're just going for the basic idea. Any question on that? So every time you have a vertical asymptote, it's going to break your graph into another section. We generally don't do more than 2 vertical asymptotes, which breaks it into 3. We will have some with just 1 vertical asymptote, which breaks it into 2. Questions on that? All right, so we're just going to try a couple of those, and that's really it. So let's try, so we did one where the degree in the top was smaller. Let's do one where the degrees are equal. It ends up looking very similar. The only difference is now your horizontal asymptote isn't at 0. Okay, let's start with the vertical asymptotes. What should I do that's going to make my vertical asymptotes easier to figure out? Well, Travis?
Factor?
Yep. Numerator or denominator?
Denominator.
Yeah, who cares about the numerator, right? Denominator. That's all we do. That's all we got to worry about for finding vertical asymptotes. And how would the denominator factor? Yep.
You can factor out x.
That's all you can do.
X parentheses 2x minus 5.
Perfect. Okay. So how many vertical asymptotes, Nick, are we going to end up with? 2. Yep. And can you tell me what my 2 vertical asymptotes will be?
0 and 2.5.
Yep. X equals 0 and x equals 2.5. Perfect. All right, let's do the horizontal asymptote. But what do we do first that helps us to get that? Yeah.
The EBM.
EBM. So let's get the EBM done. What's going to be my EBM in this case? Yep. 3 over 2. There's my EBM. So now what happens to that fraction as x approaches infinity? What does my EBM approach? Yeah, approaches 3 over 2. Yep. Okay, so let's start sketching some asymptotes. We got verticals at 0 and 2.5. So 1 at 0. I got 1 at 2.5. And I got a horizontal asymptote at 3/2, which is 1.5. Close enough. Okay, so we got all that. Now, intercepts. Well, since the numerator is kind of complicated, it's a quadratic, I don't really want to set that equal to 0 and solve it, because then I got to deal with this. And just to get the intercept, it's not even worth trying to solve a quadratic, especially if it wasn't factorable. I mean, maybe that could be factorable, but let's just focus on the other intercept, okay? So instead of letting y equal 0, we're not gonna do that one. Let's do the y-intercept. That one's always easy. Just fill in 0 for x. What do you get in the top if you fill in 0 for x? Yeah? Negative 4. And what do you get in the bottom if you fill in 0 for x? Yeah? 0. Uh-oh. So what's that mean? So we're trying to find the y-intercept. And that's what we got. So what do you think that means is going to happen? Yeah?
Maybe it won't cross the y-intercept.
Yeah, it's never going to cross the y-axis. There isn't one. You can't cross the y-axis if you have a vertical asymptote on the y-axis. Okay? So we can see that just by looking at the picture. You never can cross a vertical asymptote. So, all right. So now we just need to investigate. We've got our asymptotes. We did as much as we're going to do with the intercepts. Let's plug it in and then pick some points left and right and start seeing if we're at infinity or negative infinity. Okay. So we've got, in parentheses, 3x squared plus x minus 4. And we're going to divide by 2x squared minus 5x. Okay, so those are our old values. You can leave them and just type over them, or you can delete them. What's a value that's a little bit smaller than 0? Let's do that asymptote first. Value a little bit smaller than 0. Yep.
Negative 0.001.
Negative 0.001. Negative 8,000. So I would say when we're just before 0, as you approach 0 from the left, way down here, probably going to be way up on the other side, but let's check. Value a little bigger than 0. Yeah.
0.001.
0.001. We're up at 800. Yep. So we are way up here. Let's check the 2.5. Okay, we already know it's an asymptote, so you can't put 2.5. But what's a value that's before 2.5 as you approach it from the left side? Yep.
2.499.
2.499. So we're at negative 35,000. So almost negative 35,000. So way down. And now let's do a value that approaches 2.5 from the right side. What would be a number we could plug in for that? Yep.
2.5001.
2.5001. Okay, we're at 345,000. So we're way, way up. Since I didn't find intercepts this time, I do want to check some more points in the middle. What would be a good x value to check in the middle section? Yeah? 1. You can check 1. 1, 0. Nice point. So 1, 0. Let's also do, let's do 0.5. So 0.5, I'm a little above 1. And let's do, well, 2 might be too far down. No, I can do 2. 2, negative 5. 2, 1, 2, 3, 4, 5. Okay, so I can see what's happening in the middle. It's a very steep curve. It's going to look like this. It's going to start to curve. can go like that. So very steep in the middle. What would be another good x value to check what's happening in the upper right? Yeah.
4.
All right, let's check 4. So 4, 4 is a good point. 1, 2, 3, 4. 1, 2, 3, 4. And that's, I mean, if you want to do one more, I mean, you could, I guess you could check 10 because that's the edge of my graph. 10, 2. 10, 2. I can see perfect what's happening. It's going to curve right down. It's going to go like that. Okay. Now let's start to examine in the lower lower left. We got this point right here already. But what's, say, another good value to pick for that lower left section for x? So, Gregory, what do you think? What's a good value to pick?
Like -1.
Okay, so we do -1. We're at about -0.3. So -1, -0.3. Okay, so it's going to curve up. If you go a little further, you'll get another point that's going to show you the curve a little better. -5, almost up at 1. So 1, 2, 3, 4, 5, about right there. And now we can kind of see our curve. So it's going to start to curve and get extremely steep. In fact, it's so steep, I don't know if the calculator is really going to be able to draw that very well. Okay, it might have a hard time with it. Let's see. It might just all of a sudden stop. Yeah, that's exactly what it did. Because it got too steep to work with, the calculator basically just gave up. But we know that middle section is extremely steep. It should keep going up forever. And the section on the lower left, it should keep going down forever. That, and like that. That's what it should look like. And that's pretty much what we got. Okay. So that's how you sketch rational functions when the degrees in the top and the bottom are equal, or when the degree in the bottom is bigger. They generally have this look where there's 3 pieces as long as you have 2 vertical asymptotes. If you only have 1 vertical asymptote, then a lot of times you might get something that looks like this. Just 2 pieces. It's a little bit simpler. You don't get that middle section. Questions on that one? All right. So the last one was just like the first one where the degree in the bottom is bigger and it gave you a horizontal asymptote at 0 again. So it's pretty much the same thing. Okay, so that's homework for tonight. So on the 1 through 7, just odd. Okay, so we'll take a look at those tomorrow. Also, while you guys are in your next class, I'll post the video and I'll list the extra help. I'll list the topics that are going to be on the test, okay, for tomorrow. Also, if anybody does come for extra help, then I can do the video, and that would be posted probably by 4 o'clock. If nobody comes, then they wouldn't be able to come for extra help.